What if everything you see around you, the chair you're sitting on, the screen in front of you, even the stretch of the night sky, is just a tiny fragment of reality? What if our universe, with its three familiar dimensions, is merely a thin slice of something incomprehensibly vaster? This isn't science fiction. It's one of the most thrilling possibilities in modern physics, the idea that hidden dimensions, curled up or stretched beyond our perception, might be woven into the very fabric of existence. Think of it like this: an ant crawling on a sheet of paper sees only flatness, unaware that the paper is part of a notebook filled with countless other pages. Could we be like that ant, oblivious to dimensions that hold the keys to the cosmos' deepest secrets? For centuries, we've believed space was defined by length, width, and height, but cutting-edge theories suggest there's so much more. Imagine dimensions where gravity leaks into other realities, where parallel universes brush against ours like shadows, or where the laws of physics as we know them are just surface-level rules. Scientists call these ideas brane worlds, string theory, and compactified dimensions, concepts that sound like they're ripped from a fantasy novel, yet they're grounded in real math and observation. Picture a hologram, a flat surface that creates the illusion of depth. Now stretch that idea to the universe itself. Could all the stars, galaxies, and even time be projections from a higher dimensional realm? In this video, we're going to uncover 30 mind-bending facts about these hidden dimensions, facts that will challenge how you see reality itself. We'll explore how they could explain the mysteries of dark matter, why gravity feels so weak compared to other forces, and whether black holes might actually be portals to other layers of existence. Along the way, we'll use thought experiments that twist your perception, like imagining how a four-dimensional being would view our world with godlike clarity, or how folding space-time like origami might reveal shortcuts across the cosmos. This isn't just about science, it's about peering beyond the veil of the ordinary, into realms where the impossible starts to make sense, so buckle up. By the end, you'll never look at the universe the same way again. String theory doesn't just hint at hidden dimensions, it demands them. According to this groundbreaking framework, the universe isn't built on just the three dimensions we experience daily. Instead, it requires a staggering 10 or 11 dimensions for the math to hold together. Imagine trying to play a symphony with only half the instruments. Without those extra dimensions, the equations of string theory simply fall apart. So where are these missing dimensions, and why can't we perceive them? The answer lies in something called compactification. Picture a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line. But if you zoom in, you'd see the hose's circular surface, a second dimension, curled up so tightly it's invisible from afar. That's how theorists like Edward Witten and Brian Greene describe our reality. The extra dimensions are coiled into intricate, microscopic shapes called Calabi-Yau manifolds, structures so tiny they're a billionth of a billionth the size of an atom. These hidden shapes aren't just mathematical curiosities. They could explain why the universe behaves the way it does. Think of them as the unseen gears of a cosmic clock, influencing everything from the strength of gravity to the behavior of particles. If even one of these compactified dimensions were slightly different, the fundamental forces we rely on might not exist as we know them. String theorists argue that the vibrations of tiny, one-dimensional strings within these higher dimensional spaces determine the properties of all matter and energy. A string vibrating one way might become an electron, while another could create a quark. In this symphony of dimensions, the very fabric of reality is composed of these microscopic oscillations. But how do we reconcile this with our three-dimensional experience? Consider a butterfly trapped in a glass box. It can move forward, backward, left, right, up, or down, but it has no concept of the world outside its enclosure. Similarly, our perception might be confined to a three-dimensional brane. floating within a higher dimensional space, like a slice of bread in a vast cosmic loaf. Some theories even suggest that gravity, uniquely weak compared to other forces, could be leaking into these extra dimensions, diluting its strength in our observable universe. It's as if we're sensing only a faint echo of gravity's true power. Visualizing these higher dimensions stretches the limits of human intuition, but mathematicians use tools like Calabi-Yau manifolds' delicate, multi-dimensional shapes resembling twisted origami to map them out. If you could shrink down to the quantum scale, you might find yourself navigating a labyrinth of folded space, where every turn reveals a new direction our macroscopic senses can't comprehend. This isn't wild speculation, it's a serious attempt to unify quantum mechanics and general relativity, two pillars of physics that currently resist reconciliation. String theory's extra dimensions might just be the missing link, the hidden architecture underlying the cosmos. Long before string theory suggested 10 or 11 dimensions, two brilliant physicists dared to ask, what if just one extra dimension could solve one of science's greatest puzzles? In the early 1920s, Theodore Kaluza made a radical proposal by adding a fifth dimension to Einstein's equations of gravity. He could also explain the behavior of light. It was as if gravity and electromagnetism, the two known forces at the time, were simply different faces of the same cosmic coin. Kaluza sent his calculations to Einstein, who was initially stunned by the elegance of the idea. The math worked flawlessly, but where was this fifth dimension hiding? Enter Oscar Klein, who offered a breathtaking explanation. The extra dimension might be curled up so tightly, like a microscopic spiral staircase, that it's invisible to our everyday perception. Imagine blowing up a balloon with a tiny ant walking along its surface. From far away, the ant's path looks perfectly flat. It's only when you zoom in that you notice the curve. Klein suggested our universe might work the same way. At scales smaller than a trillionth of a meter, space could loop back on itself in this hidden fifth dimension. What's astonishing is how this tiny twist in geometry could unite two seemingly unrelated phenomena. In Kaluza-Klein theory, gravity isn't just bending space-time, it's vibrating through this compact dimension, creating ripples that manifest as electromagnetic waves. Picture throwing a stone into a pond. The splash sends out circular ripples in 2 dimensions, but in 3 dimensions, those ripples would form a spherical wave. Similarly, what we perceive as separate forces might just be different slices of a higher dimensional interaction. This wasn't just mathematical poetry, it hinted at something profound. If forces like gravity and electromagnetism could merge through geometry, perhaps all fundamental forces were facets of a single, deeper reality. While Kaluza-Klein theory eventually fell out of favor, unable to explain newer discoveries like the nuclear forces, it planted the seed for every extra-dimensional theory that followed. Modern string theory owes a debt to this early vision, where the fabric of reality isn't just stretched or warped, but elegantly folded. Think of it as the first rough sketch of a grand unified theory, scribbled in the margins of history. What's equally fascinating is how close Kaluza and Klein came to unraveling mysteries we're still grappling with today. Their compact fifth dimension echoes in contemporary ideas like braneworlds, where our universe is a 3-dimensional membrane floating in a higher dimensional space. Even the notion that particles might be vibrations in hidden dimensions resurfaces in string theory. The Kaluza-Klein breakthrough reminds us that sometimes the most revolutionary ideas aren't about adding complexity, but realizing that simplicity might lie just 1 dimension beyond what we can see. Dark matter might be the universe's most elusive ghost, invisible, intangible, yet making up nearly 85% of all matter in existence. But what if it's not hiding in the shadows of our dimensions at all? What if dark matter is right in front of us, just operating in realms we can't access? This is the spine-tingling possibility that some physicists like Harvard's Lisa Randall are exploring. Dark matter could be made of particles that only interact with us through hidden dimensions. Think of it like a radio signal. You can't see or touch the waves passing through your room, but they're there, carrying music from a station miles away. Similarly, dark matter might be all around us, vibrating in dimensions curled up so tightly that we only feel its gravitational whisper. Traditional theories suggest dark matter consists of weakly interacting massive particles, WIMP hypothetical entities that barely interact with normal matter except through gravity. But despite decades of searching, detectors buried deep underground have come up empty. That's where the extra-dimensional angle flips the script. In Randall's braneworld scenario, our universe is a three-dimensional membrane, or brane, floating in a higher dimensional space. While ordinary particles like electrons and quarks are glued to our brain, dark matter might be free to wander the cosmic bulk, drifting through dimensions we can't perceive. It's as if we're fish in a pond, unaware of creatures walking on land just above the surface. Here's where it gets even wilder. Gravity, unlike other forces, could be the only thing that leaks into these extra dimensions. That might explain why it's so weak compared to electromagnetism or the nuclear forces it spread thin across dimensions we can't see. If dark matter also leaks into these hidden realms, its particles might interact through their own version of gravity, completely bypassing our detectors. Picture a game of billiards where some balls roll off the table into another room. We'd only see the ones left behind, wondering where the others went. Randall's work suggests these hidden dimensions aren't just mathematical abstractions. They could solve multiple cosmic puzzles at once. If dark matter is darting through extra dimensions, it would explain why we've failed to catch it. It would also offer a fresh way to test these theories by looking for subtle imprints in cosmic phenomena like gravitational waves. Imagine ripples in a pond revealing the footsteps of invisible giants walking along the shore. That's the promise of this idea, turning the universe's greatest mysteries into clues pointing toward dimensions beyond our own. Quantum entanglement is often called spooky action at a distance. For a reason, particles separated by light years can instantly influence each other, as if space and time don't apply. Einstein hated this idea, calling it absurd. But what if this quantum weirdness isn't spooky at all? What if it's just physics playing out in dimensions we can't see? Picture two ants crawling on a sheet of paper that's been folded like an accordion. To the ants, their worlds seem separate, miles apart, but in reality, they're just a single fold away from touching. This is how higher dimensions could unravel the mystery of entanglement. Particles might not be communicating faster than light across our three-dimensional space. They could simply be neighbors in a hidden fourth or fifth dimension, whispering to each other through a shortcut we can't perceive. This idea isn't science fiction. It's at the heart of work by physicists like Juan Maldacena, who study the holographic principle. Imagine the universe as a cosmic game of telephone, where information isn't lost but projected from a higher dimensional reality onto our three-dimensional screen. In this view, entangled particles aren't breaking any rules. They're just following the deeper geometry of space-time, connected through folds we're blind to. It's like watching shadows on a wall. Two seemingly separate shapes might actually be cast by the same object in a higher dimensional space. Maldacena's holographic principle suggests something even more radical. Everything we experience, every star, every atom, even our own thoughts, might be a projection of information encoded on a distant two-dimensional surface. Think of it like a Blu-ray disc storing a three-dimensional movie. The disc itself is flat, but when played, it creates an immersive world. If our universe works similarly, then quantum entanglement's spookiness could just be the glitches in the projection, hints of the higher dimensional script running behind the scenes. This perspective flips everything we thought we knew about locality, the idea that objects are only influenced by their immediate surroundings. In a higher dimensional framework, close and far might be illusions, artifacts of our limited perception. Two particles could appear light years apart in our three-dimensional slice of reality, while practically holding hands in a fourth spatial dimension. It's like trying to measure the distance between 2 points on a crumpled piece of paper. Flatten it and they seem far apart, unfold it and they might be touching. The implications are staggering. If higher dimensions explain quantum entanglement, they might also hold the key to unifying physics' greatest theories, quantum mechanics and general relativity. Right now, these two frameworks describe the universe brilliantly at their own scales, but they clash violently when combined. Yet in a holographic universe where gravity emerges from quantum information encoded on a boundary, the conflict could dissolve. Suddenly, black holes' paradoxes, the nature of time, even the origin of the cosmos might look different when viewed through the lens of hidden dimensions. So the next time you hear about quantum spookiness, remember, the real magic might not be in the particles themselves, but in the unseen dimensions they're dancing through. What seems impossible in our flat, three-dimensional view could be inevitable in the full, folded geometry of reality. The holographic principle turns everything we think we know about reality inside out. Imagine stepping back from a high-definition TV screen. Up close, you see crisp, vivid images, but as you move farther away, you realize it's all just tiny pixels glowing in perfect harmony. Now stretch that idea to the cosmos. What if the three-dimensional universe we experience, every galaxy, every heartbeat, every fleeting thought, is just a breathtakingly detailed projection from a flat, two-dimensional surface at the edge of space? This isn't just a thought experiment, it's a serious theory championed by physicists like Leonard Susskind, born from one of science's most vexing puzzles, the black hole information paradox. When matter falls into a black hole, it seemingly vanishes forever, violating a core tenet of quantum mechanics that information can never be destroyed. But in the 1990s, Susskind and Dutch physicist Gerard T. Hooft proposed a radical solution. The event horizon, that invisible boundary around a black hole where not even light can escape, might not be a one-way street to oblivion. Instead, it could act like a cosmic hard drive, encoding every bit of information about what falls in, pixel by pixel, onto its two-dimensional surface. Picture a library where every book ever written is etched onto the walls in microscopic script, except here, the books are atoms, light, and even the memories of anyone who crossed the horizon. The math behind this is staggering. Just as a hologram stores a 3D image on a 2D film, the universe might encode all its depth and complexity on a distant, flat boundary. Think of it like a virtual reality headset. The visuals feel immersive and three-dimensional, but they're generated from flat, digital code. In this view, black holes aren't destroying information. They're compressing it into a format we don't yet understand, like zipping a file too advanced for our current software. What's even wilder is how this principle might apply to the entire cosmos. If a black hole's event horizon can holographically store information, why not the universe itself? Some theorists suggest our whole reality could be a projection from a two-dimensional shell at the edge of space-time, a concept that makes the brain ache. Imagine living inside a snow globe where the glass sphere's surface holds the blueprint for everything inside, every star, every law of physics, even your own consciousness. This isn't just about scale, it's about the nature of existence. Critics argue the holographic principle feels more like philosophy than physics, but experiments are catching up. Fermilab's holometer, for instance, has been searching for subtle pixelation in spacetime itself, hints that reality might have a finite resolution like a digital image. So far, the results are inconclusive, but the hunt continues. Meanwhile, string theorists like Juan Maldacena have found mathematical bridges between higher dimensional universes and their lower dimensional boundaries, lending credibility to the idea. The implications are profound. If the holographic principle holds, it could rewrite our understanding of gravity, quantum mechanics, and even free will. After all, if we're just shadows cast by data flickering on a distant surface, what does that make us? Are we the simulation or the simulators? The line between science and metaphysics blurs, but that's where the most thrilling discoveries often lie. Could civilizations beyond our imagination be watching us right now? Not from distant stars, but from dimensions we can't even perceive. This isn't just the stuff of alien invasion movies. According to cutting-edge physics, advanced beings might exist in what theorists call the bulk, the vast, higher-dimensional space that could surround our universe like an ocean around a floating leaf. Picture this: you're a two-dimensional character living on a sheet of paper. Suddenly, a three-dimensional hand reaches down, plucking an object from your world without warning. To you, it would seem like magic, an impossible violation of the rules. But to the higher dimensional being, it's just reaching across a direction you can't fathom. Now flip that scenario. What if we're the Flatlanders and something or someone is observing us from dimensions we can't access? This idea springs from the Randall-Sundrum models, brainchildren of physicists Lisa Randall and Raman Sundrum. Their work suggests our three-dimensional universe might be a brane, short for membrane, adrift in a higher dimensional bulk. Just as a piece of paper has no thickness to a 3D observer, our brain might be infinitesimally thin compared to the bulk's enormity. But here's the kicker: if other brains exist parallel to ours in this bulk space, they could host civilizations with technology so advanced it would defy our physics. Imagine a being that can see inside closed boxes without opening them, or rearrange matter in our world just by reaching around obstacles in a fourth spatial dimension. To them, our locked doors and fortified walls might be as flimsy as tissue paper. How would such beings interact with us? Think of a stick figure drawn on a page. You, as a 3D entity, could lift it off the paper, rotate it in midair, and set it back down, all without breaking the laws of its 2D world. Similarly, a bulk civilization might manipulate our reality in ways that appear supernatural. Ancient myths of gods descending from the skies or objects materializing out of thin air could take on eerie new meanings. Even modern UFO sightings, with crafts performing physics-defying maneuvers, might find explanations in higher dimensional travel, like a 4D ship dipping into our space momentarily. But before you brace for an interdimensional invasion, consider the scale. The bulk's extra dimensions might be warped or compactified in ways that make accidental contact unlikely. Just as ants on the forest floor rarely notice planes crisscrossing the sky above, bulk civilizations might not even register our brain's existence, or perhaps they're bound by their own cosmic rules, unable or unwilling to interfere. Randall-Sundrum models originally aimed to solve the hierarchy problem: why gravity is so weak compared to other forces, not to speculate about alien neighbors. Yet the implications are irresistible. If the bulk is real, it's not just a mathematical abstraction. It's a frontier teeming with possibilities, where the line between science and speculation blurs into something extraordinary. What would it take to detect such civilizations? We might look for anomalies, gravitational ripples without a source, particles appearing to vanish into other dimensions, or even patterns in cosmic microwave background radiation that suggest shadows of higher dimensional structures. Some theorists propose that dark matter's elusive nature could hint at bulk interactions, with certain particles slipping in and out of our brain like ghosts passing through walls. The truth is, we're barely scratching the surface. Our best tools, particle colliders, gravitational wave detectors, are like stone axes trying to reverse engineer a supercomputer. But the mere possibility reshapes our cosmic perspective. We might not be alone in the universe. We might be surrounded, in directions we can't point to, by realities beyond our wildest dreams. We often think of time as a straight line, past stretching behind us, future lying ahead, and the present as a fleeting moment we're perpetually moving through. But Einstein shattered this simple view when he merged space and time into a single entity, space-time. Imagine a loaf of bread where each slice represents a single moment, your now. To you, that slice feels solid, real, the only one that exists. But the loaf itself contains every possible now, stacked together in a higher dimensional structure. Here's the twist: we're stuck experiencing one slice at a time, like ants crawling along the surface of a record, unable to perceive the whole vinyl at once. This is where Minkowski diagrams come in, a tool physicists use to visualize space-time. Picture a grid where the horizontal axis represents space and the vertical axis represents time. Your life isn't just a dot moving across this grid, it's a tangled world line, a thread weaving through the fabric of reality. Every decision you make, every path you take, bends that thread in subtle ways. But here's the mind bender. In this diagram, the past and future aren't gone or unrealized, they're just directions like left and right. The entire loaf exists at once, and our inability to see beyond our slice is more about perception than physics. Why does this matter? Because if time is just one dimension in a larger structure, what's stopping others from existing? Think of a DVD. To the laser reading it, the data is a linear sequence, one frame at a time. But the disc itself holds the entire movie in a spiral of microscopic pits, a static, unchanging whole. Our experience of time might be just as limited, a single scan line across a vastly richer reality. Some theories, like block universe theory, take this further, suggesting that all moments past, present, and future are equally real, fixed in space-time like landmarks on a map. Your childhood, your next birthday, even the heat-death of the universe, they're all out there, already written. This flips everyday intuition on its head. Free will, the passage of time, even the nature of memory start to look different when viewed through this lens. If the future is just another coordinate in space-time, why does it feel so unknowable? The answer might lie in entropy, the universe's tendency toward disorder, which gives time its arrow. But entropy doesn't negate the block universe. It's just the gradient that makes one slice feel different from another, like the way a movie's plot only makes sense when played in order, even though every frame exists simultaneously on the reel. Now stretch this idea further. If space-time is a four-dimensional loaf, could there be a fifth, sixth, or 10th dimension, stacked alongside it, equally real but imperceptible? Just as a flatlander can't look up, we might be blind to directions that exist beyond our biological senses. String theorists argue these extra dimensions aren't just mathematical abstractions. They could be curled up at every point in space, like microscopic hinges between folds in reality. Picture a spiderweb glistening with dew. To us, it's a 2D surface, but to a tiny insect, each strand might harbor hidden depth. Similarly, the now we experience could be just one layer in a far more intricate tapestry. So next time you glance at a clock, remember, time isn't passing. You're moving through it like a traveler crossing a landscape that's always been there, whole and unchanging. And somewhere, perhaps in dimensions we can't yet name, other yous might be navigating their own slices, forever unaware of the loaf's full shape. Gravity is the cosmic underdog of the fundamental forces, so feeble that a tiny fridge magnet can defy the entire Earth's gravitational pull. Yet mathematically, it shouldn't be this weak. The hierarchy problem, one of physics' most nagging puzzles, asks why gravity is a trillion times weaker than electromagnetism or the nuclear forces. The answer might lie in dimensions we can't see. Picture a garden hose stretched across a football field. From the bleachers, it looks like a thin, one-dimensional line. But up close, you'd spot its circular cross-section, a hidden dimension curled so tightly it escapes casual notice. Now imagine gravity as water flowing through that hose. If the hose had microscopic leaks, some water would seep into the surrounding soil, thinning out the stream. That's exactly what could be happening in our universe. Gravity's strength might be leaking or diluting into extra dimensions, leaving only a faint trickle in our familiar three-dimensional realm. This isn't just poetic speculation. The Large Hadron Collider, humanity's most powerful microscope, has been hunting for fingerprints of these hidden dimensions. How? By searching for graviton's hypothetical particles that mediate gravity, which might momentarily vanish into higher dimensional space during collisions. Think of it like clapping your hands in a foggy valley. If some of the sound echoes into a hidden canyon, the returning noise would be quieter, with gaps in the expected pattern. Similarly, if gravitons slip into extra dimensions, physicists could spot missing energy in particle collisions, a telltale sign of dimensional bleed-through. The implications are staggering. If gravity's weakness stems from spreading into higher dimensions, it would mean we're living on a membrane, a three-dimensional island in a vast, multidimensional ocean. In this scenario, the other forces like electromagnetism are tethered to our brain, while gravity alone can traverse the bulk. It's like living in a house where light and sound stay confined to the rooms, but heat seeps through the walls into the outside world. String theory takes this further, suggesting these extra dimensions aren't arbitrary, but intricately folded into Calabi-Yau shapes at every point in space, geometrical origami, dictating the universe's fundamental rules. If proven, it would redefine not just gravity, but our entire cosmic address. Suddenly, the hierarchy problem isn't a bug in our equations, it's a feature of reality's hidden architecture, waiting to be decoded. Cosmic strings sound like something from a science fiction epic, filaments of pure energy thinner than an atom yet stretching across the entire observable universe. But these bizarre structures might be real, and they could be the scars of a violent cosmic birth. Picture the early universe not as a smooth, expanding balloon but as a frothing sea of spacetime itself, still cooling from the unimaginable heat of the Big Bang. Just as cracks form in ice as it freezes, defects might have emerged in the fabric of reality as it settled into its current state. These defects wouldn't be made of matter or energy as we know them. They'd be kinks in the very geometry of existence, like wrinkles in a crumpled bedsheet frozen into place. String theory gives this idea even wilder depth. Imagine two branes, those higher dimensional membranes we've discussed, colliding like cymbals in an 11-dimensional symphony. The shockwaves from such an impact wouldn't just ripple through space. They might leave behind cosmic strings as vibrational remnants, like the ringing silence after a bell is struck. Simulations of colliding branes show how these defects could form, vibrating strands of pure spacetime tension, each one a snapshot of the universe's most chaotic moments. Think of them as the universe's stretch marks, evidence of a growth spurt in the first trillionth of a second after creation. What's astonishing is how something so inconceivably thin could warp the cosmos on a colossal scale. A single cosmic string, just a proton's width across, could have the mass of 1,000,000 suns packed into every mile of its length. If one passed through our solar system, you wouldn't see it, but you'd feel its gravity bending light around it like a ghostly lens. Galaxies on either side of a string might appear duplicated in the sky, a cosmic mirage created by space-time itself being puckered along this invisible seam. Some astronomers have even scoured ancient light from the early universe, searching for the telltale distortions that a cosmic string's gravity would imprint on the cosmic microwave background, like finding a fingerprint on the surface of time. The eerie part, these strings could still be out there, drifting through the galaxy like spider silk on the wind. If two strings crossed, they might snap violently, releasing bursts of gravitational waves detectable across billions of light years. Others might loop into self-contained knots, collapsing into black holes or vibrating at frequencies that hum across the electromagnetic spectrum. For all we know, dark matter itself could be threaded through the universe on these invisible filaments, a web of dimensional defects left over from the birth of everything. Whether cosmic strings exist remains one of physics' great open questions, but if they do, they're more than just cosmic curiosities. They'd be living fossils from the moment reality itself crystallized into its current form, threads woven through the tapestry of space-time that might, just might, lead us back to dimensions we've yet to perceive. Black holes have long been the ultimate cosmic enigmas, regions where gravity crushes matter into oblivion, where time slows to a crawl, and where the known laws of physics simply break down. But what if these monstrous voids aren't just dead ends? What if they're gateways, twisted corridors leading to dimensions beyond our own? The idea isn't as far-fetched as it sounds. Einstein himself, alongside physicist Nathan Rosen, theorized that black holes might connect to other points in spacetime through bridges, now known as Einstein-Rosen bridges or wormholes. Picture a piece of paper folded in half with a pencil stabbing straight through both layers. To a flatlander living on the paper's surface, the holes would appear as separate, unconnected points. But in 3 dimensions, they're linked by a shortcut, a tunnel through the paper's hidden depth. That's the essence of a wormhole, a higher dimensional passage stitching distant parts of the universe together like threads in a cosmic quilt. But wormholes aren't the only way black holes might bridge realities. Enter fuzzball theory, a radical alternative from string theory that reimagines the very heart of a black hole. Instead of a crushing singularity, a point of infinite density, fuzzballs propose that black holes are tangled knots of vibrating strings, their energy smeared across a fuzzy, higher dimensional surface. Think of a black hole not as a bottomless pit, but as a dense, chaotic ball of yarn with threads fraying into other dimensions. In this view, falling into a black hole wouldn't mean annihilation. It might be like plunging into a whirlpool that spits you out into an entirely new realm. The visuals here are mind-bending. Remember the Tesseract scene from Interstellar, where Cooper floats through a labyrinth of bookshelves and moments in time. That's a glimpse of how higher dimensional pathways might look, a folding of reality where inside and outside lose all meaning. If black holes are portals, they could be threading our universe into a vast multiverse, like stitches holding together layers of an infinite cosmic fabric. Some theories even suggest that the Big Bang itself was a white hole, the opposite of a black hole, spewing matter into our universe from another dimension's collapse. Of course, there's a catch. Crossing a black hole's threshold or event horizon would likely stretch you into spaghetti like strands long before you reached whatever lies beyond. But for a civilization with mastery over space-time, or for particles immune to tidal forces, these cosmic doorways might be the ultimate transportation network. It's a dizzying thought. Black holes, once symbols of ultimate destruction, could be the universe's most dramatic bridges, silent, invisible highways winding through dimensions we're only beginning to dream of. The accelerating expansion of the universe is one of cosmology's greatest mysteries. Dark energy seems to be relentlessly pushing galaxies apart, as if space itself has a hidden engine. But what if this expansion isn't driven by some unseen force within our universe? What if it's the result of our 3-dimensional reality floating in a higher dimensional void, subtly tilting or stretching like a leaf carried by unseen currents? This bold idea emerges from brane cosmology, where our universe isn't an isolated bubble but a dynamic membrane drifting through a much larger multidimensional space called the bulk. Picture a water strider gliding across a pond. Its ripples and movements aren't solely the result of its own actions but are influenced by the deeper water beneath it. Similarly, dark energy's push might not originate within our brain at all. It could be the gravitational tug of another brain floating parallel to ours, or the curvature of the bulk itself flexing around us. The ekpyrotic universe model takes this even further. Proposed by physicists Paul Steinhardt and Neil Turok, It suggests our Big Bang wasn't a singular explosion from nothingness, but a collision between two branes in higher dimensional space. Imagine two sheets of paper floating in a dark room, drifting closer until they smack together with incredible energy. That impact wouldn't just create sound or heat, it could birth entire universes, inflating them with the kinetic energy of the collision. In this view, the cosmic expansion we observe today might be the aftershock of that primordial crash, our brain still vibrating like a drumhead struck long ago. Unlike traditional inflation theory, which relies on a mysterious inflattened field, ekpyrosis frames the universe's growth as a higher dimensional phenomenon, one where dark energy is merely our brain settling into its new position in the bulk. The implications are staggering. If the bulk's geometry influences our brain's expansion, we might be able to detect higher dimensions indirectly by measuring subtle anomalies in how galaxies recede. Astronomers have already noticed that dark energy's strength appears frustratingly constant across space, unlike other forces that weaken with distance. This could make sense if its source isn't inside our universe but outside it, like a steady breeze blowing against our brain from the bulk. Some versions of this theory even predict that our brain isn't perfectly flat. It might have tiny warps or folds that distort gravity's pull, explaining why certain galaxy clusters seem to move faster than our models predict. Visualizing this is a challenge, but think of a flag rippling in the wind. From close up, the fabric seems to stretch and contract on its own, but zoom out and you see the wind's invisible hand shaping every motion. If higher dimensions are the wind shaping our brain's expansion, then dark energy isn't an energy at all, just the shadow of something far grander. Future telescopes like the European Space Agency's Euclid mission might find clues by mapping the universe's large-scale structure with unprecedented precision, searching for patterns that hint at our brain's interaction with the bulk. Could this rewrite our cosmic origin story? If the ekpyrotic model holds, the Big Bang wasn't the beginning, just a chapter in an endless cycle of brain collisions. Each collision resets the universe, wiping the slate clean while preserving traces of previous cycles in the gravitational waves that ripple through the bulk. It's a vision of reality where dimensions we can't perceive don't just exist, they actively shape everything we thought we understood. The universe's expansion might not be a solo performance after all, but part of a multidimensional symphony we're only beginning to hear. At the smallest scales imaginable, far tinier than the nucleus of an atom, spacetime isn't smooth or solid. It churns, it bubbles, like ocean foam whipped up by a tempest. The fabric of reality itself becomes a seething quantum froth, where dimensions flicker in and out of existence in bursts of unfathomable energy. This isn't poetic exaggeration, it's the prediction of loop quantum gravity, a framework where space isn't continuous but made of minuscule, indivisible grains. Imagine zooming in on a seemingly smooth sheet of paper until you see the jagged fibers, each one twisting and knotting. At this level, the universe isn't just textured, it's alive with fluctuations, a fractal dance of geometries that might hide dimensions beyond our perception. These fleeting extra dimensions wouldn't resemble the vast, uncurled spaces of string theory. They'd be ephemeral, like soap bubbles forming and popping in Planck-scale chaos, each one a tiny window into a direction we can't normally access. The idea stems from quantum mechanics' inherent unpredictability. At scales a billionth of a proton size, particles blink in and out of existence, borrowing energy from nothingness. If matter can do this, why not space-time itself? Picture a simmering pot of water. Steam rises in fleeting tendrils, each one a temporary structure in the air. Similarly, quantum foam might allow microscopic extra dimensions to surge upward from the quantum boil before collapsing back into the background hum of reality. Loop quantum gravity takes this further, proposing that space is woven from interconnected loops. Think of a cosmic mesh where each thread carries a quantum of area. In this view, spacetime isn't just grainy, It's dynamic, with nodes and links constantly reconfiguring like a hyper-dimensional game of cat's cradle. When these loops tangle in just the right way, they could pinch open micro-wormholes or birth pocket dimensions lasting mere fractions of a second. It's as if the universe is built on a scaffold of invisible threads, and sometimes those threads knot into shapes that defy our everyday experience of space. Visualizing this requires abandoning all intuition. If you could shrink down to the Planck length, about 10 to the power of -35 meters, you wouldn't find serene emptiness. You'd witness a storm where dimensions are born and dissolved in flashes too brief for any clock to measure, where the concept of here and there blurs into probabilistic haze. Some theories even suggest these fluctuations could leave faint imprints on light traveling across the cosmos, subtle scattering patterns that might one day reveal the foam's structure. What's wild is how this connects to black holes. At their singularities, where general relativity predicts infinite density, loop quantum gravity sees something else: a rebound. The collapsing fabric of spacetime hits a limit compressed to the smallest possible grain and then bounces. In that critical moment, extra dimensions might flare like sparks from a forge, offering a glimpse into the deeper architecture of reality. It's a reminder that the universe's most extreme places, black holes, the Big Bang, the quantum foam, aren't just dead ends. They're laboratories, places where the hidden layers of existence peel back, if only for an instant, to show us how much we've yet to understand. What if entire universes, each with their own stars, planets, and maybe even versions of you, were hovering just millimeters away, separated by a gap so infinitesimal we couldn't see or touch it? This isn't the plot of a sci-fi thriller, it's a serious possibility in braneworld cosmology. Picture two sheets of paper suspended in midair, perfectly parallel but never touching. To a flatlander living on one sheet, the other sheet's existence would be completely invisible, its world hidden by a direction up that the flatlander can't perceive. Now replace those sheets with three-dimensional membranes, or branes, drifting through a higher dimensional space called the bulk. Suddenly, the idea of parallel universes becomes less about distant galaxies and more about realms that could be closer than the screen in front of your face. Gravity holds the key to this mind-bending arrangement. Unlike light or matter, which are bound to their home brane like ink to paper, gravity might be the only force that leaks into the bulk. Imagine shouting into a pillow. The sound stays muffled, but the weight of the pillow still presses down on your lap. Similarly, while electromagnetic waves and nuclear forces remain trapped within a brane, gravity's influence could seep into adjacent dimensions, subtly tugging on neighboring universes. This explains why we haven't bumped into our parallel neighbors. Their photons, quarks, and cosmic rays can't reach us, but their gravitational whispers might. The numbers are staggering. If the bulk's extra dimension is compactified, curled up like the circumference of a soda straw, those parallel branes could be a mere millimeter apart in higher dimensional space. To us, that millimeter would be invisible, folded into a direction we can't point to or move through. A civilization living on a neighboring brane might evolve under the same physical laws, their Milky Way mirroring ours, all while oblivious to our existence. It's like living in an apartment building where each floor is an entire universe, the walls between them made of pure geometry. Could we ever detect these shadow worlds? Some physicists suggest looking for tiny deviations in gravity's strength at submillimeter scales, places where its pull might weaken or ripple unexpectedly as it bleeds into adjacent branes. Experiments using ultra-sensitive torsion balances, like those at the University of Washington, have already hunted for such anomalies, though no smoking gun has emerged yet. Others propose that cosmic collisions between branes, like the one posited in the ekpyrotic universe model, might leave imprints in the cosmic microwave background, faint scars from a long-ago encounter with our dimensional neighbors. The implications rewrite our cosmic address. If parallel branes exist, the multiverse isn't a far-flung collection of disconnected bubbles. It's a stacked deck of realities, each one brushing against the next in directions we can't fathom. Dark matter's elusive nature could even find an explanation here. What if it's just ordinary matter on a nearby brane, its gravity leaking into ours like distant music through a shared wall? The idea teeters on the edge of metaphysics, but the math holds up. We might be living in a cosmic neighborhood so densely packed with realities, the only thing separating us from infinite versions of ourselves is a gap smaller than a grain of sand and a dimension we've yet to name. The shape of hidden dimensions isn't just abstract geometry, it's the hidden code that writes the laws of physics. Take Calabi-Yau manifolds, those intricate six-dimensional shapes string theorists believe are curled up at every point in space. These aren't just mathematical ornaments, they're cosmic tuning forks, vibrating in ways that determine everything from the mass of an electron to the strength of the forces holding atoms together. Picture a flute with an elaborate pattern of holes. Blow into it and the air vibrates through those openings, producing distinct musical notes. Now imagine the flute is a Calabi-Yau shape, and the notes it produces aren't sounds, they're particles. The electron, that's one vibrational pattern, the quark another. Even the ghostly neutrino might just be a whisper of resonance echoing through these folded dimensions. Here's where it gets wild. The exact number of holes in a Calabi-Yau manifold, its topological handles, could dictate how many particle families exist in our universe. Some configurations might allow only 3 generations of quarks and leptons, matching what we observe. Others could predict dozens, rendering our cosmos unstable or unrecognizable. It's as if the universe's blueprint were etched into these higher dimensional forms, their geometry selecting which particles get to exist and how they behave. Scientists like Brian Greene liken this to a cosmic sorting hat, except instead of assigning wizards to houses, Calabi-Yau shapes assign vibrations to particles, granting them mass, charge, and identity. To grasp how profound this connection is, consider the humble electron. Why does it weigh what it weighs? In string theory, its mass isn't an arbitrary number. It's a reflection of how tightly strings can stretch and vibrate within the Calabi-Yau's labyrinthine folds. A slightly different shape, a twist here, a loop there, and the electron might have been 1,000 times heavier or lighter, altering chemistry, starlight, even the very possibility of life. The same goes for forces. The electromagnetic force's strength, for instance, could hinge on how easily strings winding around these shapes interact, like threads braiding through a multidimensional loom. Visualizing these shapes is a challenge, but mathematicians render them as swirling, hyperdimensional sculptures, some resembling intricate honeycombs, others like quantum origami with endless pleats and folds. Each configuration is a universe of possibilities, a unique instrument in the cosmic orchestra. The mind-bending part: if we could probe space-time at scales 1 billion times smaller than a proton, we might find these structures everywhere, humming silently beneath the surface of reality. Critics argue that without experimental proof, Calabi-Yau manifolds remain beautiful speculation. But advancements in particle colliders and precision gravity measurements inch us closer to testing these ideas. If future experiments uncover anomalies in particle behavior or unexpected symmetries, they might be echoes of these hidden geometries, footprints of dimensions we can't yet see. Until then, the shapes linger in equations, silent architects of a reality far richer than our senses perceive. What if every particle in your body, every electron, every quark had a hidden twin, a shadowy counterpart vibrating in dimensions just beyond our reach? This is the spine-tingling premise of mirror matter, a theoretical form of particles that could exist in parallel dimensions, interacting with our world only through the faintest gravitational tugs. Think of it like living in a house with invisible roommates. You never see them, never bump into them in the hallway, but sometimes you feel the floorboards creak under unseen footsteps. In this case, the footsteps would be subtle gravitational anomalies, hints that entire galaxies of mirror stars and planets might be hovering right beside us, separated by a direction we can't point to. The math behind this is as elegant as it is bizarre. Just as your reflection in a mirror flips left and right but otherwise matches your movements, mirror particles could obey the same fundamental laws as ours but with flipped properties. Electrons might carry positive charge instead of negative, or the weak nuclear force could operate in reverse. Some models even suggest that mirror matter could explain the enigma of sterile neutrinos, those ghostly particles detected only by their gravitational whispers, as if they're slipping in and out of our dimension like cosmic spies. Picture a theater stage where actors perform under bright spotlights, unaware of an identical play unfolding in the darkness just behind the backdrop. The sterile neutrinos, they'd be the rare actors who briefly step into both worlds, visible only as fleeting silhouettes. Now imagine a split-screen universe. On one side, our familiar reality with its delicate balance of physics constants that allow stars to shine and life to emerge. On the other, a mirrored version where gravity is stronger, light moves slower, or atoms bond in alien ways. In that shadow realm, carbon might never form, rendering biology impossible, or it could give rise to exotic life forms built from elements we've never dreamed of. The chilling part, we'd have no way to know. Mirror planets could orbit mirror stars right through our solar system, their presence betrayed only by the faintest wobbles in our spacecraft's trajectories. The hunt for mirror matter isn't just theoretical. Experiments like the European Space Agency's LISA mission, designed to detect gravitational waves, might catch distortions caused by mirror black holes colliding in higher dimensions. Underground labs have searched for particles that oscillate between our world and the mirrored one, like neutrons turning into their shadowy counterparts and back again. Even the mysterious Planet 9, a hypothetical giant planet lurking at our solar system's edge, could, in some models, be a mirror world object exerting gravitational pull without reflecting a single photon of light. What's mesmerizing is how mirror matter ties into string theory's web of ideas. If Calabi-Yau manifolds dictate particle properties, their mirror-symmetric counterparts could birth entire shadow sectors of reality. It's as if the universe built a secret annex, identical in structure but just out of phase, like a piano playing the same melody in a higher octave, vibrating through dimensions our ears can't hear. Whether these shadow particles are out there remains one of physics' most tantalizing maybes. But if they are, they'd rewrite not just our understanding of matter, but the very definition of reality itself. We've been taught that the universe began with a bang, a single, unfathomably hot explosion of space, time, and energy. But what if the Big Bang wasn't a bang at all? What if it was a crash, a violent collision between two cosmic membranes drifting through a higher dimensional void? This is the heart of the ekpyrotic universe scenario, a radical alternative to traditional inflation theory that reimagines our cosmic origins not as a solitary spark, but as the aftermath of a multidimensional traffic accident. Picture two enormous sheets of metal suspended in a dark room, hurtling toward each other until, bam, they slam together with unimaginable force. Now replace those sheets with branes, three-dimensional worlds floating in a bulk of extra dimensions, and the energy of their collision doesn't just create sound or heat. It births entire universes, inflating them like balloons in the shockwave of impact. This idea flips the script on inflation, the prevailing theory that our universe underwent exponential expansion a fraction of a second after the Big Bang. Inflation solves many cosmic puzzles, like why the universe is so uniform, but it relies on a mysterious inflattened field, a cosmic gas pedal we've never detected. The ekpyrotic model, proposed by physicists Paul Steinhardt and Neil Turok, offers a different solution. Instead of an inflattened field, it's the kinetic energy of colliding branes that stretches space, smoothing wrinkles and seeding galaxies. Think of it like kneading dough, where inflation puffs up the dough with yeast, braneworld collisions flatten it with a rolling pin. The visuals here are mind-bending. If you could peer into the higher dimensional bulk moments before the collision, you'd see two ghostly membranes, each potentially home to its own stars, civilizations, even alternate versions of you drifting closer until their gravitational pull becomes irresistible. When they meet, the energy doesn't annihilate matter but transmutes it, like two oceans merging into a single, churning sea. The fireball we call the Big Bang might just be the flash of our brain reheating, its energy dissipating into the three-dimensional space we now call home. Unlike inflation's one-and-done expansion, the ekpyrotic scenario suggests this could happen cyclically, braneworlds rebounding after each collision, endlessly creating and recreating universes in an eternal cosmic dance. What's astonishing is how this idea tackles the same cosmic riddles as inflation, but with higher dimensional geometry instead of hypothetical fields. The uniformity of the universe, that's not luck, it's the branes flattening against each other like pages in a book being pressed together, the distribution of galaxies. Ripples left by quantum vibrations in the pre-collision branes stretched across the sky like fingerprints on blown glass. Even dark energy, the mysterious force accelerating cosmic expansion, could be the slow realignment of our brain as it drifts toward its next collision. Critics argue that without direct evidence of extra dimensions or parallel branes, the ekpyrotic model remains speculative, but hidden clues might lurk in gravitational waves, the ripples in space-time from the universe's earliest moments. Traditional inflation predicts a specific gravitational wave signature, while ekpyrosis would leave a different pattern, like comparing the aftershocks of an explosion to those of an earthquake. Future observatories like the Laser Interferometer Space Antenna LISA could sift through this cosmic static, hunting for echoes of a collision rather than a bang. Until then, the ekpyrotic universe stands as a thrilling reminder. Our origin story might not be written in the language of solitary creation, but in the grammar of dimensions we've yet to see, where beginnings are collisions, and the Big Bang is just one note in an infinite, multidimensional symphony. Gravity's puzzling weakness has long baffled scientists. Why is it so pathetically feeble compared to other fundamental forces? A fridge magnet can defy Earth's gravitational pull with ease, yet mathematically, gravity should be far stronger. The answer might lie in cosmic spillage. Imagine standing in a shower, watching water droplets spray from the showerhead. Some hit your skin, but others vanish into the air, misting away unseen. Now picture gravity as that water and our three-dimensional universe as the shower floor. The droplets that land represent the gravity we experience, weak and diluted, while the rest. They're leaking into extra dimensions, drifting into the cosmic air we can't perceive. This showerhead analogy isn't just poetic, it's rooted in serious physics. Gravitons, the hypothetical particles thought to carry gravitational force, might not be confined to our brain like other particles. Instead, they could propagate freely through the higher dimensional bulk, thinning out their influence in our observable universe. It's like trying to catch sunlight with a net. Most photons stream right through the holes, leaving only a faint warmth in your hands. If gravitons slip into extra dimensions, their strength in our world would dwindle, explaining why gravity feels like the runt of the fundamental forces. The hunt for this leakage is already underway. Scientists have designed exquisitely sensitive experiments to measure gravity at microscopic scales, where extra dimensions might warp its pull. Picture two tiny gold weights suspended near each other in a vacuum. At distances smaller than a hair's width, if gravity suddenly weakens more than predicted, it could signal a hidden dimension siphoning off gravitons like water spiraling down a drain we can't see. Experiments like these, conducted at institutions like the University of Washington, have so far found no definitive proof, but the precision required is staggering. Detecting extra dimensions this way would be like noticing a single missing grain of sand from a beach. String theory adds another layer to this mystery. The geometry of those hidden dimensions, whether tightly curled Calabi-Yau shapes or expansive brane worlds, could act like gravitational sieves, determining how much leaks and how much stays. A slight twist in their configuration might mean the difference between a universe where gravity crushes stars into black holes instantly and one where it barely holds planets in orbit. That's the precarious balance we inhabit, a cosmos where gravity's feebleness isn't a bug but a clue, a fingerprint of dimensions hiding in plain sight. Future particle colliders might push the boundaries further. If gravitons truly escape into the bulk, high-energy collisions could produce them momentarily before they vanish, leaving behind telltale gaps in energy measurements. It's like smashing two clocks together and finding some gears mysteriously missing evidence they've bounced into a space beyond the workbench. Until then, gravity's weakness remains one of the universe's most tantalizing breadcrumbs, hinting at a reality far grander than the three dimensions we call home. Hidden dimensions might be the universe's ultimate peacemakers, the unseen mediators that could finally end physics' century-long family feud. For decades, scientists have struggled to reconcile the four fundamental forces: gravity bending space-time, electromagnetism lighting up our world, and the strong and weak nuclear forces gluing atoms together. Each operates by its own rules, like separate languages spoken under one cosmic roof. But superstring theory whispers a radical solution, that at unimaginably high energies, like those just after the Big Bang, these forces weren't strangers at all. They were one. Picture the periodic table of elements, a tidy grid where hydrogen, gold, and uranium each have their place. Now imagine a similar chart, not for matter, but for the messengers of force, photons carrying light, gluons binding quarks, W and Z bosons controlling radioactive decay, and gravitons weaving spacetime's fabric. Today, these particles seem as different as can be, but crank the energy up to trillions of degrees and something extraordinary happens. Just as heating ice transforms it into water, then steam, these force carriers begin to merge, their differences melting away in the searing heat. Superstring theory suggests this unification isn't just a blur. It's the revelation of a deeper symmetry, a hidden harmony playing out across 10 dimensions. Here's where the extra dimensions come in. Think of the forces as musical notes. In our three-dimensional world, they sound distinct: a deep bass for gravity, a piercing violin for electromagnetism. But add 6 more curled-up dimensions, and suddenly, these notes blend into a chord. The vibrations of tiny strings threading through these higher dimensional shapes could explain why forces appear separate at low energies. We're only hearing fragments of the full composition. A string vibrating one way might manifest as a photon in our world, while another twist could become a gluon, like a single piano string producing different notes depending on where it's struck. The implications are staggering. At the universe's birth, when energies were high enough to unfurl all dimensions fully, there was no distinction between gravity and light. There was only a single superforce, a primordial unity that shattered as the cosmos cooled and dimensions curled in on themselves. Like shards of a broken mirror, each force reflects a piece of that lost symmetry. Some theorists even speculate that the exact way these dimensions compactified, whether they formed intricate Calabi-Yau shapes or simpler loops, determined the strengths and properties of the forces we now observe. A slight difference in their geometry and electromagnetism might have been weaker, or the strong force might not bind nuclei at all. Visualizing this requires a mental leap. Imagine holding a prism up to sunlight. It splits the beam into a rainbow of colors. The superforce is the original white light, and the 4 fundamental forces are the separated hues. Hidden dimensions act like the prism's facets, bending the unified force into the spectrum we recognize today. Experiments at particle colliders like the Large Hadron Collider hunt for traces of this unity, searching for tiny deviations in particle behavior that might hint at extra dimensions influence. So far, no smoking gun, but the mathematical elegance keeps physicists hooked. What's breathtaking is how this framework doesn't just patch together forces, it redefines them as different faces of the same multidimensional phenomenon. Gravity's weakness, a symptom of it leaking into higher dimensions, the bizarre quantum behavior of particles, ripples from strings dancing through folded geometry. Even the dream of a theory of everything begins to look plausible when forces aren't competing explanations, but chapters in a single, higher dimensional story. The cosmos might not be a collection of disjointed rules after all, but a symphony we've been hearing one note at a time. Time loops aren't just sci-fi fantasy, they might be hidden in the geometry of the universe itself. In 1949, Einstein's friend and fellow genius Kurt Gödel dropped a bombshell. He found a solution to general relativity where the universe rotates, twisting spacetime so severely that time bends back on itself like a Möbius strip. Imagine drawing a line on that twisted paper loop. Your pencil would eventually return to where it started, with no beginning or end. Gödel showed that in such a cosmos, you could theoretically travel into your own past just by moving far enough through space, following a path called a closed time-like curve. But here's the catch: our universe doesn't seem to rotate, and these time loops require conditions we don't observe. Unless, of course, higher dimensions are doing the twisting behind the scenes. This is where the fifth dimension comes in. Picture a subway system where trains run in loops, but some tracks dip through tunnels you can't see from the platform. In our normal four-dimensional spacetime, time travel creates infamous paradoxes. What if you kill your grandfather before you're born? But add a fifth dimension, and suddenly, that loop might bypass the paradox by taking the tunnel, weaving through a direction we can't perceive. Think of it like this: ants crawling on a Möbius strip live in a flat, two-dimensional world, unaware that their reality is secretly twisted in three dimensions. Similarly, a fifth spatial dimension could allow time loops to exist without violating causality, their paradoxes smoothed out by geometry we're blind to. String theorists like Kip Thorne have explored this idea with wormhole shortcuts through spacetime that could function as time machines. But wormholes require exotic matter to stay open, a substance with negative energy that's never been observed. Hidden dimensions offer a more elegant fix. If gravity can leak into higher dimensional space, perhaps time can too. Gödel's rotating universe might not describe our cosmos, but in a five-dimensional bulk, even a static brain could harbor time loops if the larger geometry rotates around it. Visualize a record spinning on a turntable. The grooves our spacetime seem stationary, but the rotation of the whole system creates unseen forces. A closed time-like curve in this setup wouldn't require moving faster than light or finding exotic matter, just a hidden dimensional twist. The most tantalizing part: this isn't pure speculation. Quantum particles already exhibit behavior that defies classical notions of time, like retrocausality, where effects seem to precede causes. Some interpretations suggest these particles are sampling timelines that loop through higher dimensions, their paths resolving paradoxes by existing in superposition until observed. It's as if time, at its core, isn't a straight highway but a tangled ball of yarn, with threads darting into dimensions we can't see. Future experiments with entangled particles or precise gravity measurements might uncover hints of this temporal geometry, tiny knots in the fabric of reality where time takes a detour through the fifth dimension. So the next time you imagine a time machine, don't think of a glowing DeLorean. Think of a universe folded like origami, where past and future touch along hidden creases, and where the key to unlocking time's secrets might lie in directions we're only beginning to imagine. What if the universe isn't just projected from higher dimensions but programmed by them? The holographic principle already suggests that all our 3D reality might be encoded on a distant 2D surface like cosmic source code. But take that idea one step further, and you arrive at something even more unsettling. Our entire existence could be a simulation orchestrated by higher dimensional beings, with the holographic boundary acting as the universe's hard drive. Think of the most advanced video game you've ever played. Now imagine the game's world doesn't just simulate physics, but is physics. It's every pixel governed by rules written in a dimension beyond the screen. This isn't just speculative fiction. Philosopher Nick Bostrom's famous simulation argument lays out a chillingly logical case. If civilizations eventually gain the power to create conscious simulations indistinguishable from reality, the number of simulated minds would vastly outnumber biological ones. Statistically, we're more likely to be those simulations than the original creators. Now layer this with the holographic principle, and the simulation hypothesis gains a geometric twist. Higher dimensional beings wouldn't need to render our universe pixel by pixel. They could generate it holographically, storing all information on a lower dimensional boundary and letting the 3D illusion emerge naturally, like a game engine extrapolating a 3D world from compressed data. Consider how video games optimize performance. Instead of loading every detail at once, they render only what the player sees, filling in textures as needed. Our universe might operate similarly. Quantum mechanics already shows particles don't have definite properties until observed, an oddity that makes perfect sense if reality is being computed on demand. The double-slit experiment, where particles act as waves until measured, could be seen as a cosmic form of lazy loading, where the simulation only crunches the numbers when someone's looking. Even the speed of light, the universe's processing speed limit, might be a constraint imposed to prevent system overload. The Matrix gave us a visceral metaphor: human brains in vats fed artificial stimuli. But a holographic simulation would be far more elegant. Higher dimensional engineers wouldn't need to fabricate every atom. They'd just need to encode the universe's underlying laws and let it self-assemble like a procedurally generated galaxy. The 2D boundary storing our reality's data would function like a cosmic QR code, with every gravitational wave and supernova just a projection of its intricate patterns. Even glitches like particles teleporting in quantum tunneling or dark energy's unexplained push might be artifacts of the code, hints that we're running on higher dimensional hardware. Critics dismiss this as unfalsifiable, but physicists like Silas Bean have proposed ways to test it. Just as pixels impose a resolution limit, a simulated universe might have a fundamental graininess to spacetime at the smallest scales. Others suggest looking for mathematical shortcuts in cosmic constants, round numbers, or symmetries that hint at programmer convenience, the most haunting possibility. If we ever prove we're in a simulation, it might trigger a shutdown, or worse, an update. Whether metaphor or reality, the simulation hypothesis reshapes how we see existence. If higher dimensions are the server racks running our universe, then black holes might be garbage collectors compressing deleted data, and consciousness itself could be an emergent process of the rendering. It's a dizzying thought: the stars, the laws of physics, even your memories, all just shadows of code written in a language we can't yet speak, running on hardware we can't yet see. In the vast cosmic ocean, everything should drift randomly, galaxies swirling like leaves caught in a gentle breeze. Yet something bizarre is happening on the largest scales we can observe. Entire clusters of galaxies, thousands of them, are streaming in the same direction at breakneck speeds, as if tugged by an invisible hand. Astronomers call this phenomenon dark flow, and it defies everything we know about cosmic expansion. It's like watching scattered candles in a dark room suddenly tilt their flames toward some unseen window, all pointing the same way. The culprit could be an immense gravitational presence lying beyond the edge of our observable universe, or perhaps something even stranger, a parallel brane in higher dimensional space exerting pull from a direction we can't perceive. Maps of this mysterious motion reveal clusters hurtling toward a single patch of sky near the constellations Centaurus and Hydra, moving at speeds exceeding 2 million miles per hour. The kicker, there's nothing massive enough in that direction to explain it. No supercluster, no cosmic void, just ordinary space. That's where the braneworld hypothesis flips the script. Picture two massive ships sailing parallel to each other in thick fog. You can't see the other ship, but you feel its wake gently rocking your boat. Similarly, if another brane universe floats near ours in the higher dimensional bulk, its gravity could be leaking across the dimensional divide, creating these unexplained currents in our cosmic sea. Some theorists suggest this gravitational signature might be the aftermath of a long-ago brane collision, like ripples from a pebble tossed into a pond next to ours, subtly disturbing the water's surface. Others propose it's evidence of a mother brane, an even larger membrane whose gravity warps our universe's structure from outside. The math is daunting. These models require precise alignment of extra dimensions and brane tensions, but the payoff could rewrite cosmology. Imagine if dark flow isn't just an anomaly. It's our first glimpse of the bulk's architecture, the hidden scaffolding that connects our universe to others. Skeptics argue it could be residual motion from the Big Bang's uneven expansion, or flaws in how we measure cosmic microwave background radiation. But as telescopes like ISA's Euclid map galaxy motions with unprecedented precision, the mystery only deepens. If dark flow persists in future surveys, we might be staring at something far more profound than measurement error. We could be seeing the gravitational shadow of a neighboring reality, a cosmic neighbor waving from just beyond the veil of perception. What makes this especially tantalizing is how it mirrors ancient navigation techniques. Sailors once found unknown islands by watching where seabirds flew at dusk, trusting their paths revealed land beyond the horizon. Today, we're cosmic sailors tracing the flight of galaxies toward shores we can't yet see. Whether dark flow leads us to unseen dimensions or reshapes our understanding of gravity itself, one thing's certain: the universe is pulling us toward revelations we're only beginning to sense. Quantum tunneling is like watching a marble phase through a wall defying logic, yet happening constantly at the subatomic scale. Here's how it might secretly involve hidden dimensions. Imagine you're a rat trapped in a flat 2D maze, scurrying along corridors with no way over the walls. From your perspective, escape is impossible until someone lifts you into the third dimension, where walls become mere lines you can hop over effortlessly. That's the essence of tunneling. An electron facing an energy barrier it shouldn't overcome doesn't smash through. It seemingly vanishes from one side and reappears on the other, as if taking a detour through a direction we can't see. This isn't magic, it's quantum mechanics with a dimensional twist. Particles aren't just particles, they're also waves, smeared across space with probabilities rather than fixed positions. When an electron's wave function brushes against a barrier, there's a tiny chance it leaks through like fog seeping under a door. But here's the kicker: calculations show some tunneling events happen faster than light could cross the same distance in our three-dimensional space. That's where compact dimensions come in. If space has microscopic folds, those curled-up Calabi-Yau shapes, particles might not be teleporting so much as taking hyperdimensional shortcuts, like ants crawling through the crumpled grooves of a paper ball instead of trekking across its flat surface. The Casimir effect adds tantalizing evidence. When two metal plates are placed nanometers apart in a vacuum, they're inexplicably pulled together. Why? Because the space between them is so tiny, only certain quantum fluctuations, virtual particles popping in and out of existence, can fit, while larger fluctuations thrive outside. The result, a pressure differential that nudges the plates. But some theorists argue this isn't just about particle physics, it's geometry. Those fluctuations might be borrowing energy from compact dimensions, their brief existence enabled by folds in spacetime we can't perceive. Picture a pond freezing over. Cracks form where the ice is thinnest, but beneath the surface, hidden currents shape their paths. Similarly, tunneling particles could be surfing microscopic ripples in higher dimensional foam. What's wild is how this reshapes our view of reality. If particles routinely duck into extra dimensions, even momentarily, then the universe isn't just around us. It's threaded with hidden layers we're only now learning to sense. Forget teleportation sci-fi. Nature's been doing it all along, right under our noses, or more accurately, through dimensions just beyond our grasp. Imagine an ocean where every drop isn't water, but an entire universe. Not just any ocean, a frothing, infinite sea of higher dimensional foam, each bubble a separate cosmos with its own laws of physics, its own version of stars and atoms, even its own arrow of time. This is the string theory landscape, a mind-numbing vista where 10 to the power of 500 possible universes, that's a 1 followed by 500 zeros, float like soap suds in a multidimensional bathtub. The numbers are so vast they dwarf every grain of sand on Earth, every star in the observable cosmos, and buried among that near-infinite array might be a bubble where gravity is stronger, where light moves slower, or where time runs backward, realities as different from ours as a black hole is from a butterfly. What's propelling this cosmic carbonation? A process called eternal inflation. Picture a bottle of soda shaken violently, where new bubbles keep nucleating endlessly in the foam. Now replace the soda with the fabric of space-time itself, expanding exponentially faster than light, and the bubbles with pocket universes. Quantum fluctuations in this hyper-inflating medium create seeds, tiny regions where expansion slows just enough for matter and energy to condense into a stable universe like ours. But the frenzy never stops. Beyond the boundaries of our observable universe, the inflationary froth continues spawning new realities endlessly, each one sealed off from the others like apartments in an infinite skyscraper, their windows pointing in directions we can't see. The visuals here stretch comprehension. If you could hover outside this higher dimensional foam, you might witness universes budding off like droplets on a spiderweb, some colliding and merging, others drifting apart forever. String theorists like Leonard Susskind argue that this isn't just metaphor. The landscape emerges naturally from the mathematics of Calabi-Yau compactifications. Those six-dimensional shapes we discussed earlier, their exact configuration at the moment of nucleation could determine whether a universe gets 3 generations of quarks or 7, whether dark energy is strong enough to rip spacetime apart or so weak that galaxies clump into superstructures we can't even imagine. The variety isn't random, it's the combinatorial explosion of different ways extra dimensions can fold. Here's where it gets personal. In a multiverse this vast, copies of you near perfect or wildly divergent might exist in countless bubbles. A version where you never stumbled upon this video, another where dinosaurs still rule Earth, yet another where the laws of physics made life impossible entirely. This isn't just speculative fun, it's a potential solution to one of cosmology's deepest puzzles, why our universe seems improbably fine-tuned for life. If every possible physics setting gets its own universe, then of course we'd find ourselves in one where conditions allow our existence, a cosmic version of the anthropic principle. The alternative, believing in a single, perfectly calibrated universe by sheer luck, like rolling a million dice and getting all 6s on the first try. Critics dismiss the landscape as untestable, a philosophical cop-out. But clues might lurk in the cosmic microwave background, patterns that could hint at our universe brushing against another bubble long ago, like a scar from an ancient collision. Others propose that the cosmological constant's eerily precise value, which keeps our universe balanced between runaway expansion and collapse, is evidence of selection effects across the multiverse. After all, in a sea of 10 to the 500 possibilities, even the most improbable outcomes become inevitable somewhere, the most dizzying thought. This hyperdimensional foam might not even be the full picture. Some models, like the brane multiverse, stack entire landscape, oceans, in higher dimensional bulk space, creating layers upon layers of reality. It's as if we've spent centuries studying a single snowflake, only to step back and realize we're standing in a blizzard that never ends. Whether the multiverse is real or just a beautiful mathematical phantom, one thing's certain: our universe feels a lot less lonely and a lot stranger when viewed as one tiny bubble in a foam we're only beginning to fathom. Consciousness might be the universe's most sophisticated dimension unfolding tool, a biological instrument capable of perceiving realities beyond the three spatial dimensions we navigate daily. Mystics and psychedelic explorers have reported encounters with geometries so complex they defy conventional description: kaleidoscopic fractals, infinite tessellations, and spaces that curve in ways our everyday logic can't pass. What if these visions aren't mere hallucinations, but fleeting glimpses into the higher dimensional scaffolding of reality? Consider the work of neuroscientist Carl Pribram, who proposed that the brain itself might operate like a hologram, encoding memories and perceptions not in specific locations, but across the entire neural network. Just as a hologram reconstructs a 3D image from 2D interference patterns, our minds could be decoding multidimensional information from a deeper, implicate order, one where spacetime's hidden layers are folded into the fabric of thought itself. The parallels between these subjective experiences and string theory's mathematical frameworks are eerie. During deep meditation or psychedelic states, users consistently describe encountering structures reminiscent of Calabi-Yau manifolds, those intricate, multi-dimensional shapes theorized to curl up at every point in space. One striking example is the recurring motif of the cosmic serpent, a luminous, self-replicating lattice reported by indigenous ayahuasca drinkers and modern psychonauts alike. Its twisting, hyperdimensional form mirrors the way Calabi-Yau geometries vibrate through 6 compactified dimensions, generating the fundamental particles of our universe. Could these visions be the brain's imperfect translation of higher dimensional data, like a radio tuned just enough to catch fragments of a distant broadcast? Neural networks add another layer of intrigue. Advanced AI models, when visualizing high-dimensional data, often project it into 3D representations that look uncannily like quantum foam or string theory's curled-up dimensions. The brain's 100 trillion synapses might be doing something similar, taking the raw code of reality and rendering it into a form our biology can process. Think of a video game console. It receives binary inputs but outputs immersive worlds. Our consciousness could be the user interface for a cosmos far richer than we perceive, with psychedelics temporarily disabling the display settings that filter out extra dimensions. This isn't just poetic speculation. Quantum physics hints that observation itself might collapse higher dimensional probabilities into the 3D world we experience. In the double-slit experiment, particles behave as waves until measured, as if they're sampling multiple dimensions before choosing one to manifest. Mystical traditions have long claimed that consciousness shapes reality. Perhaps it's more accurate to say consciousness selects which slice of a multidimensional reality becomes tangible. The Tibetan Buddhist concept of the bardo, a liminal space between dimensions, or the Kabbalistic tree of life, with its 10 sephiroth representing cosmic layers, could be ancient maps of this terrain, intuitive grasps at truths now edging into scientific view. Even our language betrays a latent understanding. We speak of expanding our minds or transcending limits, verbs that imply movement through dimensions. Artists like M.C. Escher, whose impossible staircases and infinite loops play with perception, might have been intuiting higher dimensional topology long before mathematicians formalized it. The brain's default mode network, which quiets during mystical experiences, could function like a dimensional filter, keeping us anchored to consensus reality. When that filter dissolves, as in near-death experiences or deep meditation, the mind might briefly access the full, unfiltered spectrum of existence. Critics argue these are just neurological glitches, the brain's chaos trying to make sense of overload, but the consistency across cultures and epochs is hard to dismiss. Whether through DMT's machine elves, the geometric visions of Sufi mystics, or the holographic resonance of Pribram's model, the message is the same: reality is vaster than it seems, and consciousness might be the key to unlocking its hidden doors. Future research could test this by mapping neural activity under psychedelics against string theory's predictions, hunting for patterns that match Calabi-Yau vibrations or higher dimensional symmetries. Until then, the most tantalizing clue lies in our own minds, the persistent feeling, across time and tradition, that we're perceiving only a fraction of what's truly there. Long before particle colliders or quantum equations, ancient civilizations were already grappling with the idea that reality extends beyond what the senses reveal. Take Plato's famous allegory of the cave prisoners chained since birth, mistaking shadows on a wall for reality. Those flickering silhouettes, he argued, were mere projections of a richer, three-dimensional world outside the cave. What if our entire universe is just like those shadows, a lower-dimensional echo of a higher, more complex reality? Plato's intuition mirrors modern holographic theory with uncanny precision, suggesting that even 2,500 years ago, the human mind sensed there was more to existence than meets the eye. Halfway across the world, Hindu cosmology was mapping out dimensions with startling specificity. Ancient texts like the Bhagavata Purana describe the universe as an 11-layered structure, with each layer governed by different laws and beings. The parallels to M-theory, string theory's most advanced variant, which requires 11 dimensions, are almost unsettling. Hindu sages spoke of lokas and talas, realms stacked like floors in an infinite cosmic building, accessible only through advanced meditation or divine grace. These weren't just metaphors, they were detailed cosmographies, complete with descriptions of how beings in higher dimensions could perceive lower ones effortlessly, much like how a 4D being would view our 3D world as an open book. Then there's the Kabbalistic tree of life, a mystical diagram from Jewish tradition that maps the universe as 10 interconnected spheres or sephiroth, each representing a different aspect of creation. Modern mathematicians have noted how these geometries resemble Calabi-Yau manifolds, the six-dimensional shapes at the heart of string theory. The tree's intricate pathways, where divine energy flows between dimensions, echo the way strings vibrate through folded space to generate particles. Even the Kabbalistic concept of tzimtzum, the contraction of divine light to make space for creation, finds eerie resonance in theories like the ekpyrotic universe, where branes collide and withdraw to birth new realities. Sacred art adds another layer to this puzzle. Tibetan mandalas, when overlaid with string theory's visualizations, share startling fractal similarities. Both depict reality as nested, vibrating patterns radiating from a central void. The flower of life, an ancient geometric motif found from Egypt to China, mirrors quantum foams bubbling spacetime at the Planck scale. How could cultures separated by millennia and continents land on such similar imagery? One provocative explanation: these traditions weren't just guessing. Through deep contemplation or altered states, their seers might have glimpsed the scaffolding of existence itself, interpreting higher dimensional truths through the symbolic language of their time. This isn't about romanticizing the past or dismissing modern science. It's about recognizing a thread woven through human history, the persistent sense that reality is grander than it appears. Today, we probe these mysteries with equations and particle detectors. Ancient cultures used myths, meditation, and sacred geometry, but both point toward the same horizon, dimensions beyond our ordinary perception, waiting to be uncovered. Perhaps the most profound lesson here is humility. If civilizations without telescopes or microscopes sensed hidden layers of reality, What else might we be missing, even with all our technology? The universe's secrets have always been whispering to us, sometimes in the language of mathematics, sometimes in the symbols of a mystic's vision. The challenge is learning to listen. The flickering lights in the sky that we call UFOs might not be aliens crossing interstellar space, but entities slipping through dimensions right beside us. Imagine you're a character in a 2D world confined to a flat plane when suddenly a 3D apple descends into your reality. To you, it would appear as a dot that grows into a circle before shrinking and vanishing, defying all known physics. Now replace that apple with an object or being moving through a fourth spatial dimension intersecting our own. Their sudden apparitions, impossible maneuvers, and disappearances could simply be higher dimensional travelers dipping in and out of our perceptual range like fingers through water. This interdimensional hypothesis flips the classic extraterrestrial narrative. Instead of spacecraft traversing light years, these visitors might be commuting through folded space, their tech appearing to defy gravity because they're not moving in our 3 dimensions linearly, but stepping around obstacles via higher dimensional shortcuts. A craft could seemingly vanish from one location and reappear instantly elsewhere, not by breaking light speed, but by moving through a direction we can't perceive. Even their infamous falling leaf descent, often reported in UFO encounters, mirrors how a 4D object would intersect our 3D plane at changing angles before departing like a soap bubble popping out of existence. The parallels to Flatland are uncanny. In Edwin Abbott's 1884 thought experiment, a 3D sphere passing through a 2D world would appear as a circle materializing from nowhere, expanding, then contracting to nothing. To flat beings, this seems supernatural, but to the sphere, it's just movement along an ordinary to them up-down axis. Similarly, if a 4D craft entered our atmosphere, we'd only perceive slices of its full structure, creating illusions of morphing shapes or cloaking. Reports of metallic orbs splitting into smaller units might reflect higher dimensional topology, like watching a hypercube rotate, its 3D shadow appearing to fragment impossibly. Contrast this with traditional extraterrestrial theories. Interstellar travelers would face known physics constraints, acceleration forces crushing pilots, cosmic radiation, the sheer energy required for light-speed travel. But interdimensional visitors sidestep these hurdles. Their journey isn't across space, but through it, like crawling through the folds of a rug rather than walking its length. Even the famous Tic-Tac UFOs recorded by U.S. Navy pilots exhibit behavior that aligns eerily with higher dimensional movement, instantaneous acceleration, no visible propulsion, and trajectories that ignore inertia as if they're unconstrained by our plane's rules. Skeptics argue this is just dressing up mythology with string theory jargon, yet the math holds surprising plausibility. Kaluza-Klein particles arising from compactified dimensions could theoretically interact with our matter briefly before rolling up back into higher space, leaving behind the radiation anomalies often detected in UFO hotspots. Even the Pentagon's Advanced Aerospace Threat Identification Program has explored warp drives and wormholes alongside traditional propulsion, hinting that defense researchers take dimensional hypotheses seriously. Cultural echoes add intrigue. Indigenous traditions worldwide speak of star people emerging from portals or mirrors, descriptions that feel less like metaphor and more like eyewitness accounts of higher dimensional transit. Modern UFO lore's obsession with interdimensional beings might be an instinctive grasp at truth's physics is only now formalizing. Perhaps the Grey's large, black eyes aren't adaptations for dim starlight, but sensory organs evolved to perceive dimensions we can't. Ultimately, the interdimensional angle doesn't disprove extraterrestrial origins, it expands the canvas. Advanced civilizations may have mastered dimensional travel alongside spaceflight, turning the universe's hidden layers into highways we're only beginning to suspect. Next time you see a UFO report, consider The truth might not be out there in distant star systems, but inches away in a direction we've yet to learn to point toward. Fractals aren't just mesmerizing digital art, they might be the ghostly imprints of dimensions we can't yet perceive. Take the Mandelbrot set, that infinitely intricate thumbprint of God, where every zoom reveals new layers of complexity. No matter how deep you dive into its swirling tendrils and seahorse tails, the patterns never simplify. This endless self-similarity hints at something extraordinary. Within its two-dimensional frame, the Mandelbrot set somehow encodes more information than our three-dimensional space should allow. It's as if we're staring at a shadow cast by a higher dimensional object like a stick figure, trying to comprehend the 3D hand that created its flat silhouette. The mathematics behind this is both beautiful and eerie. When generating a fractal, simple equations iterate themselves into mind-boggling complexity through feedback loops. But here's the twist: these equations often describe processes that can't fully unfold in our limited spatial dimensions. A coastline's fractal roughness, for instance, has a fractional dimension somewhere between 1D and 2D because its crinkles pack so much detail into linear space. Now stretch that idea further. What if quasi-crystals, those exotic materials with patterns that never exactly repeat, are actually 3D slices of higher dimensional lattices? Scientists discovered this shocking possibility when trying to explain how certain metal alloys diffract X-rays in impossible five-fold symmetries, a geometric arrangement that can't exist in ordinary crystals. The solution: model these structures as projections from a six-dimensional space where perfect symmetry exists before being flattened into our reality. Visualize it like this. Imagine rolling a 5D hypercube through our 3D world. At each moment, we'd only see a changing 3D cross-section, a series of shapes that morph and reconnect impossibly. Fractals might work similarly, their infinite complexity arising because their higher dimensional shapes being squashed into fewer dimensions, creating information-rich folds like an origami masterpiece compressed between glass. Even the way fractal antennas in your smartphone pack long reception paths into tiny spaces mirrors this dimensional trickery engineering, exploiting mathematical ghosts of extra dimensions to bend the rules of physics. The most profound implication: nature might be using fractals as a workaround, a way to cram higher dimensional processes into our limited 3D playground. Quantum foam's turbulence at the Planck scale, the branching networks of neurons in your brain, even the large-scale structure of galaxy clusters all exhibit fractal properties that suggest they're operating at dimensional depths beyond what we perceive. Next time you lose yourself in a fractal zoom video, remember, you're not just watching cool math, you're glimpsing the universe's cheat codes, hints that reality's source code runs on dimensions we've only begun to imagine. The Large Hadron Collider isn't just smashing particles, it's probing the very fabric of reality, and in the process, it might accidentally create something extraordinary: microscopic black holes. These wouldn't be the planet-swallowing monsters of sci-fi, but fleeting, quantum-scale singularities that vanish in a puff of Hawking radiation before they could harm a single atom. How? The answer hinges on those hidden extra dimensions we've been exploring. If gravity leaks into higher dimensional space, as some theories suggest, then at the extreme energies of particle collisions, space-time itself might warp just enough to pinch off a tiny black hole, a cosmic hiccup lasting fractions of a nanosecond. Picture two grains of sand colliding at nearly light speed. In our familiar three dimensions, their impact would never warp space-time enough to form a black hole. But if extra dimensions are curled up at every point like microscopic loops woven into reality's fabric, the collision's energy could suddenly spread out into those hidden directions, concentrating gravity's pull to a critical threshold. It's like pressing a needle into a stretched sheet. Normally, the sheet just bends, but if you fold it tightly enough, the needle's pressure can puncture through. Similarly, a high-energy proton collision in the LHC might, for an instant, pierce the veil of our dimensionality, creating a black hole smaller than a proton but denser than a neutron star. Before alarm bells ring, no, these wouldn't devour the Earth. Hawking radiation ensures their demise. Black holes aren't eternal. They slowly evaporate, leaking energy as they shrink. The tinier the black hole, the faster it vanishes. A micro-black hole with the mass of, say, a mountain compressed into a space a billionth of a meter wide would radiate away its entire existence in less time than it takes light to cross an atom. The LHC's potential black holes would be even lighter, evaporating before they could interact with anything nearby. It would be like striking a match in a hurricane. The flame flickers out before it can spread. Stranger still, these micro-black holes wouldn't even look like the cosmic voids we imagine. Visualizing one in action, you'd see a vanishingly small distortion in the detector, a brief burst of particles radiating outward in all directions, the signature of a singularity blinking into existence and dissolving into quantum foam. Advanced simulations show this as a shimmering sphere of energy, collapsing inward like a dying star in fast forward, its Hawking radiation painting the detector's sensors with a unique fingerprint. Scientists at CERN actively hunt for these patterns, knowing that if found, they'd be smoking gun evidence for extra dimensions. Skeptics argue that if extra dimensions exist at scales the LHC can probe, we'd have noticed their effects in cosmic rays or neutron stars. But the collider's precision offers something nature's chaos doesn't: control. By tuning collision energies and angles, physicists can test specific models of higher dimensional gravity, like the Randall-Sundrum braneworld scenario, which predicts black hole production at energies just beyond the LHC's current reach. Future upgrades might cross that threshold, turning the world's most complex machine into a portal for the universe's most enigmatic phenomena. So while the LHC hasn't yet spat out a black hole, its attempts are far from futile. Even null results refine our understanding, tightening the constraints on where or how those hidden dimensions might be curled. Whether the collider ultimately reveals them or not, the mere possibility reshapes our cosmic perspective. The same forces that bind stars and planets might, under the right conditions, rip open doorways to dimensions we're only beginning to fathom, all in the blink of a detector's eye. Vacuum decay isn't just physics jargon, it's the ultimate cosmic reset button, a scenario where the very rules of our universe could rewrite themselves in an instant. Picture a frozen lake on a winter morning. The ice seems solid, unshakable, until somewhere beneath the surface a single air bubble shifts. That tiny disturbance triggers a crack, then a fracture, then an unstoppable wave of liquid water reclaiming its domain. Now replace the lake with spacetime itself, and the ice with our current vacuum state, what physicists call the false vacuum. Just like that ice, our universe might exist in a fragile, temporary configuration, waiting for one quantum fluctuation to shatter the illusion of stability. Here's the nightmare scenario. According to quantum field theory, the vacuum isn't empty, it's a seething quantum foam where particles pop in and out of existence. The energy of this vacuum state determines the fundamental constants of our reality. The speed of light, the strength of gravity, even the dimensionality of space itself. But what if our vacuum isn't the lowest possible energy state? Imagine rolling a marble along a hill dotted with valleys. The marble might get stuck in a shallow depression, thinking it's reached the bottom, unaware of a deeper chasm just beyond the ridge. Our universe could be that marble perched precariously in a false valley. If something, a high-energy particle collision, a quantum tunneling event, knocks the marble loose, a bubble of true vacuum could form where the laws of physics operate under radically different rules. Inside this bubble, space-time wouldn't just change, it might unravel. The three spatial dimensions we know could unfurl into higher ones, like a crumpled sheet of paper suddenly flattening to reveal hidden creases. Gravity might strengthen overnight, instantly collapsing stars into black holes. electromagnetism could flicker out, dissolving atoms like sandcastles in a tide. The speed of light might slow to a crawl, freezing chemical reactions mid-process. None of these changes would violate physics. They'd simply reflect a new, more stable vacuum state with its own dimensional blueprint. The terrifying part, this bubble would expand at light speed, rewriting reality faster than any warning signal could travel. One moment, Earth exists. The next, it's part of a hyperdimensional realm where our concepts of life, matter, and time no longer apply. Could this happen? The math says yes, but with caveats. The probability of spontaneous vacuum decay in any given year is astronomically low, on the order of 1 in 10 to the power of 100. That's like rolling a die with more zeros than atoms in the observable universe and landing on one. Yet given infinite time and assuming our vacuum is indeed metastable, it becomes inevitable. Some theorists argue it may have already happened elsewhere, that beyond our cosmic horizon, entire regions of the multiverse could be undergoing vacuum decay right now, their dimensional fabrics recrystallizing like ice spreading across a pond. We wouldn't know until the wave front hit because by definition nothing, not light, not information, can outrun it. There's a haunting beauty to this idea. Just as ice ages give way to spring, vacuum decay could be the universe's way of refreshing itself, shedding old dimensions like a snake sheds skin. The process wouldn't be destruction, but transformation, a higher dimensional renaissance where new physical laws birth forms of matter and energy we can't begin to fathom. Advanced civilizations might even attempt to trigger it deliberately, engineering a controlled phase transition to access energies or technologies locked away in the true vacuum. Of course, for us three-dimensional beings, it'd be the ultimate Faustian bargain, unleashing a new cosmic order at the cost of everything we've ever known. So while vacuum decay remains speculative, it forces us to confront the staggering fragility of reality. The dimensions we take for granted, the constants we rely on, they might not be fundamental truths, but local conditions as ephemeral as frost patterns on a windowpane. The next time you gaze at the night sky, consider this. Somewhere out there, in the quantum static between stars, the seeds of a new dimensional order might already be stirring, waiting for their moment to rewrite the cosmos. Human intuition is a marvel crafted by millions of years of evolution to navigate a world of predators, prey, and the occasional falling coconut. But here's the catch: our brains are hardwired for 3 spatial dimensions. Up, down, left, right, forward, backward, that's the mental toolkit we've been given. Throw a 4th spatial dimension into the mix and our neural wiring short circuits. It's like trying to explain color to someone born blind. The framework simply isn't there. This isn't just a limitation, it's a cosmic irony. We're creatures trapped in a 3D fishbowl, trying to comprehend an ocean that might have 10, 11, or even 26 dimensions. Take the tesseract, the 4D analog of a cube. In our world, a cube casts a 2D shadow, a square. But in 4 dimensions, a tesseract would cast a 3D shadow, and what we see is a mind-bending structure of nested cubes, seemingly folding in and out of themselves. To a 4D being, this shape would be as simple as a child's block, but to us, it's a hallucinogenic puzzle. Try rotating one in your mind's eye, and you'll hit a wall, the infamous dimensional barrier. Our brains lack the neural architecture to visualize movements along a 4th axis, leaving us stuck interpreting higher dimensions through clumsy analogies and mathematical abstractions. This isn't just an intellectual curiosity, it's a roadblock for physics. Einstein famously leaned on thought experiments, using trains and elevators to conceptualize relativity. But when it comes to extra dimensions, even geniuses falter. Richard Feynman once admitted that nobody truly understands quantum mechanics, they just get used to the math. The same applies here. We can write equations describing 10-dimensional space, but internalizing those concepts, that's like trying to smell a symphony. Yet hope isn't lost. Enter artificial intelligence and virtual reality, two technologies bridging the gap between abstract math and human perception. AI systems, untethered by biological constraints, can model higher dimensional spaces with ease. Researchers at MIT have used neural networks to visualize Calabi-Yau manifolds, those six-dimensional shapes central to string theory, projecting their intricate folds into forms our brains can pass. Meanwhile, VR takes this a step further, allowing users to step inside 4D environments. Imagine wearing a headset where you can reach out and manipulate a tesseract, watching it morph as you rotate it along the fourth axis. Tactile feedback gloves could simulate the sensation of touching hyperdimensional objects, training your brain to recognize patterns evolution never prepared it for. The implications are profound. If we can simulate higher dimensional perception, we might finally grasp phenomena like quantum entanglement or dark matter's hidden dance. Mysteries that seem magical in 3D could become intuitive in 4D or 5D. Think of it like this: flatlanders living in a 2D world would find a knotted rope inexplicable until they're lifted into the third dimension, where the knot structure becomes obvious. Similarly, our cosmic puzzles might unravel when viewed from the right dimensional vantage point. But here's the humbling truth: even with tech aiding us, we'll never fully perceive higher dimensions as naturally as we do our own. At best, we'll develop a mathematical intuition, a subconscious fluency in equations that hint at realities beyond our senses, and maybe that's enough. After all, we've already mastered other invisible realms: radio waves, magnetic fields, the quantum vacuum through tools and math. The dimensions we can't see are just the next frontier, waiting for us to decode their secrets, one hypercube at a time. So the next time someone dismisses extra dimensions as fantasy, remember, so was the concept of Earth orbiting the Sun once. Our brains may be limited, but our curiosity isn't. And with AI and VR as our guides, we're closer than ever to peeking behind the universe's dimensional curtain. From colliding brains birthing universes to gravity slipping through unseen dimensions like water through a sieve, the possibilities we've explored today aren't just science fiction, they're legitimate keys to unlocking the cosmos' deepest secrets. Imagine a reality where black holes are doorways, where dark matter is just ordinary matter hiding in plain sight but one dimension over, and where the entire universe might be a holographic projection from the edge of space-time. These aren't wild guesses, they're theories grounded in advanced mathematics and bold observations, offering elegant solutions to physics' most frustrating puzzles. Why is gravity so weak? Maybe because it's leaking into higher dimensions. What's the true nature of quantum entanglement? Perhaps particles are whispering to each other through folded space-time. Even the Big Bang itself could be rewritten as a clash of cosmic membranes in a multidimensional void. Carl Sagan once reflected on humanity's dimensional blindness with his flatland analogy. Imagine beings living in a two-dimensional world, unable to conceive of up or down until a three-dimensional visitor lifts them into the vastness above. We might be those flatlanders right now, oblivious to dimensions that could reshape everything we know. The most thrilling part, we're not just passive observers. With particle colliders probing microscopic black holes, telescopes hunting dark flow anomalies, and AI mapping Calabi-Yau manifolds, we're inching closer to glimpsing the full symphony of reality, not just the notes we've been able to hear. So what's your favorite dimension-twisting theory? Do you think we'll ever experimentally prove braneworlds or catch a graviton red-handed as it ducks into the fifth dimension? Drop your thoughts below, and if you're craving more mind-bending journeys to the edges of physics, don't forget to subscribe. The universe has way more layers than we've uncovered, and the next revelation might be just one click or one extra dimension